Hello dear friends, welcome to the lecture of geometry. We are studying the right line, and in this lecture we shall study conditions for a line to lie in a plane. I have written the result to be obtained here, and after we shall first obtain this result and then we shall solve the problems on it. So the result is to find the conditions for the line. This is the symmetrical equation of line, and in the plane this is the general equation of the plane. Now, when we say a line lies in the plane, so suppose this is the plane and a line is in the plane. So this is the plane of the board, and every line drawn on this board lies in that plane. So that means the line will be of this form. This is the line which lies in the plane, and we want to find the condition. So that means every point of the line would lie in the plane. So we write the derivation of this first here. The line lies in the plane. If the line lies in the plane, or if the line lie on the plane, then every point of the line is a point of the plane. This meaning is simple. If the entire line is in the plane, then every point on the line is also a point of the plane. Now, what is a point of the line? See, from this equation we know the general point of the line can be obtained by equating this to r, and thus the point will be RL plus x1, mr plus y1 and nr plus z1. So therefore a point, thus any point, and the coordinates of the point will be LR plus x1, MR plus y1 and NR plus z1, lies on the plane. This is the point on the line that we have considered by equating each ratio to r. R is any number. For any value of r, the point can be obtained, and there are infinitely many points on the line. So if r varies, the point will change, and thus every point is given by this, or any point of the line is given by these coordinates, and this lies on the plane. Thus this point lies on the plane means what? A point lies on any surface means the point's coordinates must satisfy the equation. So this implies this will imply A into x means A into LR plus x1 plus B into MR plus y1 and plus C into NR plus z1 plus D is equal to 0. We put the point's coordinate in the equation of the plane. Now we can simplify this. So simplifying this, what we shall get? This we will take r common from the first terms of each bracket, and that is r into, in bracket what will remain, AL plus BM from this BM, and here CN plus CN in first bracket, and in the remaining terms A into x1 plus B into y1 plus C into z1 plus D is equal to 0. So this is the resulting equation. Now this equation must be true for every value of r, and this is possible only if this bracket is 0 and this bracket is 0. So that is r into 0 plus 0 will be equal to 0. So this is true for every value of r. and this implies both the bracket must be 0, because r is not fixed, and r can change. As the point changes, the value of r changes. R is any value, and this implies the first bracket is 0, means AL plus B into M plus C into N is equal to 0. The first condition. And the second is A into x1 plus B into y1 plus C into z1 plus D is equal to 0. Now thus these are the two conditions for a line to lie in the given plane. Now what the first condition says, what is this? Sum of product is equal to 0. Now we see what are ABC. ABC are the direction ratios of normal to the plane. And what are LMN? LMN are the direction ratios of the line. And that means the normal to the plane is perpendicular to the line. See, normal will be this one, and if it is perpendicular to the plane, it will be perpendicular to every line drawn in the plane, or every line of the plane. So if I draw infinitely many lines on this plane of the board, and normal to this plane of the board will be like this, so it will be perpendicular to every line. So that we have considered, and so we can see if this is the plane, then normal to the plane will be like this, and this is perpendicular to every line drawn on the plane. So that is the meaning of the first condition. And now what is the meaning of the second condition? The second condition says A into x1 plus B into y1 plus C into z1 is equal to 0. That means the point x1, y1, z1, which is a point of the line. This is the equation of line passing through the point x1, y1, z1. And therefore that is a point on the line, that is also the point of the plane, and that is what we have written. Every point of the line is point of the plane, and thus this is the meaning of second condition, geometrical meaning of second condition. So we can state these two conditions. Geometrically, the first condition says that the normal to the plane is perpendicular to the line. First, geometrical meaning of this, the normal to the plane is perpendicular to the line. And second, every point of the line is a point of the plane. So thus we have obtained two conditions which are to be remembered. If that a line lies on the plane or lies in the plane, then these two conditions must be satisfied. Now we shall write a corollary for this. Equation of a line, equation of how to obtain the equation of plane, that is about how to obtain equation of plane containing the given line. So I shall write here. Equation of a plane containing the line. We have to find equation of this plane containing this line. or equation of the plane, or it may be any plane, so we write a plane. Equation of a plane containing the line. The line is the same, x minus x1 divided by L, etc. is. Now we shall write the result directly. Now what is the equation of plane? The plane contains this line, means the plane contains this point x1, y1, z1, and we know how to write equation of a plane passing through the point x1, y1, z1. So instead of a small abc, we may consider capital ABC, because small abc are used or that is there for the equation of plane itself. But suppose capital ABC are the DRS of the normal, and then the equation of a plane containing the line can be written as A into x minus x1 plus B into y minus y1 plus C into z minus z1 is equal to 0. And what is the next condition? So this is that meaning is x1, y1, z1 equation of plane passing through the point x1, y1, z1. We have written this earlier in the chapter of plane. Any plane passing through a given point can be written in this form. And what is the second condition? The second condition means here the first condition. So the normal to this plane must be perpendicular to this line. What are the DRS of the normal? A, B, C. Instead of small abc, we have written capital ABC. We may write small abc also. And where the condition is A into L plus product of sum of product of these DRS, A into L plus B into M plus C into N is equal to 0. So this is the simple way to write equation of plane. Equation of plane is this one, and with this condition. Now one more condition must be given, and then we can find the values of ABC, or proportional values of ABC. So the condition may be the point on the plane may be given, and from that we can find the values of solving these equations. We shall find the values of ABC. Now this will be more clear when we are solving the problems. Now see, we will solve the problems. First problem is, what is the first problem? Find the equation of the plane. Find the equation of the plane passing through a plane containing this line and passing through this point. Now we shall make use of this corollary, just we have written. So solution for first problem. So equation of the plane, required plane is equation of the plane containing the line is of the form. Now see, it is simple to write A into x minus x1. See, what is x minus x1 here? The equation is of this form. So x minus x1 means x plus 1 here. These are the values of L, M, N. So we should note it. And is of the form A into x minus x1 means the numerator, that is x plus 1, plus B into y minus y1 means y minus 3, and plus C into the numerator for the third ratio z plus 2 is equal to 0. So this we shall suppose as 1, where what is the second condition? AL plus BM plus CN is 0. Now A, B, C are, we are considering these are direction ratios of normal. And what is LMN? LMN are these values. You compare the equation with this, the symmetrical equation. This is the value of L, this is the value of M, and this is the value of N. So where A into L means A into minus 3 plus B into 2 and plus C into 1 is equal to 0. So thus we have obtained the, we have written the equation of plane passing containing the line, and that is by the corollary of these two forms we have written. But what we need is the values of ABC, and to get the values of ABC, see the problem, there is one more condition is given. The plane contains this line, and the plane passes through the point, or the plane contains this point means the plane is passing through this point, or the point is on the plane. Given that the point is 0, 7, minus 7 is on the plane, 1. This is the plane, equation of the plane. We must have to write equation of the plane containing the line. It's equation of the plane containing the line. So what is the equation of the plane? 1, and this point lies on this plane 1. So therefore this implies see, put x is 0, a into 0 plus 1 plus b into y is 7 minus 3, and plus c into z is minus 7 plus 2 is equal to 0. And what that gives? This gives a into 1 plus b into 4 and plus c into minus 5 is equal to 0. We suppose this equation as second and this as 3. Now we need the values of ABC. For that purpose we solve second and 3. So we solve second and 3. Solving 2 and 3. We get. Now see how to solve 2 and 3. We use Cramer's rule in the form of determinant, and we write a divided by C for second and third. A, hide the column of A and write the coefficients of B, that is 2, 4 and then 1 minus 5 column wise. 2, 4, 1 minus 5 is equal to B, and for the determinant of B we have to hide B column, and we have to write this column first, 1 minus 5. Otherwise we have to write here negative sign. 1 minus 5 and then minus 3, 1. And C divided by. See, second and third is to be observed. So hide this terms of C and write the coefficients of AB column wise, minus 3, 1. We have done this earlier also. Minus 3, 1 is the first column, 2, 4 is the second column. And what are the values of A, B and C? See, this is minus 10, minus 4, minus 14. This is 1 and minus 15. This is positive in the product. And in the expansion of the determinant, 1 minus 15, again minus 14. And the third is minus 12, minus 2, that is again minus 14. Or thus this term can be divided out or multiplied throughout by minus 14. We will get that A upon 1 or A, B, C are equal. That is A divided by 1 is equal to B divided by 1 is equal to C divided by 1. These are the values, and thus we can take the values of ABC as 1, 1, 1, and we put these values in equation 1. So putting A is equal to B is equal to C is equal to 1 in equation 1, we get, and see the equation of the plane will be obtained now, and that is 1 into x plus 1 plus 1 into y minus 3 and plus 1 into z plus 2 is equal to 0. These are proportionate values here. In particular, the values are all equal, and therefore we have written this. They may be different. So that is, this will be x plus y plus z, and you see the constant 1 minus 3, that is minus 2 and plus 2 cancels and is equal to 0. This is the required equation of the plane. This is the plane. Equation of the plane containing the given line. So thus we obtain equation of plane containing the given line. But further, the solution is not complete. We have to next show that this line lies in the same plane, means this plane that we have obtained. Next, what is the line given? Next, the line given is, further line is this one, x. It is x, and we can write it in symmetrical form, x minus 0 divided by 1, in this form, x minus x1 divided by L. Here it is only x that can be written in this form. Then 7 minus y, we must write y minus y1. So we shall multiply by minus 1 at numerator and denominator, and that becomes y minus 7 divided by minus 3. It must be in this form. And z plus 7, so that can also be written as z minus minus 7 divided by 2. Yes, this is the line, and we have to show that this line lies in this plane. Suppose this is the equation next we should consider as 4. Third equation was written earlier, and this line lies in the plane. What is the condition of all? There are two conditions for equations of a line, or a line lie in the given plane. First we have written AL plus BM plus CN is equal to 0. Then we see that here for this line, L is 1, M is minus 3 and N is 2. And what is the point? X1 is 0, Y1 is 7 and Z1 is minus 7. And we shall check whether the condition is satisfied or not. And we have the condition first is AL, capital A into L. What are the values of capital ABC? 1 for this plane. Also, A is equal to B is equal to C is equal to 1. And we see that first A into L plus B into M plus C into N is equal to, this is the first condition that we must have. In place of small abc, we are using capital ABC. That is the change in notation, and we must be familiar for change in the notation. We should understand it, and because in mathematics we use many notations. In place of small abc, capital ABC are used. So no confusion should be there. So this must be equal to 0. Now check whether it is 0. A is 1, and what is L is also 1. So 1 into 1 plus B is also 1, and M is minus 3, and what is C is 1, and what is N is minus 2. So what is this value is 1 minus 3, and what is the value of N is 2, not minus 2, but it is 2. And we may see it is 3 and minus 3, 0. And second is, what is the second condition? A into x1. The equation of the plane is this. x plus y plus z is 0, and this point x1, y1, z1 must be on the equation of 4. So therefore x1 is 0, 0 plus y1, that is or we may write a into x1 plus b into y1 plus c into z1 and plus d. Here d is the constant is not there, and that is plus d is equal to this must be equal to 0. This is equal to, now what is a? A is 1. What is x1 is 0, and plus b is 1, y1 is 7, and c is 1, z1 is minus 7, and d in the equation of the plane is absent, 0. And what is this value? This value is also 0. You may see that 0 plus 7 minus 7, and this is equal to 0. So thus the two conditions that we have obtained in the derivation of conditions, that is AL plus BM plus CN is 0, and the second condition was A into x1 plus b into y1 plus c into z1 plus d is equal to 0. Here for that this equation of the plane d is 0, and thus this shows that the line lies on the plane. So this shows this line lie on the plane that we have obtained, x plus y plus z is equal to 0, and thus this completes the solution of the problem. Now the second and third problem you should try, because these are part of this solution. Show that this line lies in the plane, and to show the line lies in the plane only we need these two conditions to show. A into L plus b into m plus c into n is equal to 0. Show that. What will be the values of L, M, N that we should note? Here L will be 1, and this must be multiplied by minus 1. So it must be y minus 8 divided by minus 2, and this is z minus 0 divided by 1. So that means L is 1, M is minus 2, and Z is 1. And what are the values of A, B, C? These are the coefficients of x, y, z are the values of A, B, C. Capital A can be taken as 1, 2, 3, and show their sum of product is 0. And second condition is like this, A into x, etc. What is x1? X1, write the equation in this form, symmetrical form, this equation. So x1 will be minus 10. Here it is y minus 8 means y1 will be 8, and here z1 will be 0, and show this also satisfies. That means for the second problem you should show the first and the second condition. So that you can try yourself. And what about the third? Third is the exactly same that we have solved. Find the equation of the plane. We have to find the equation of the plane containing this line and this point. So first we may write the equation in the form A into x minus x1, and x1 point here is minus 2, y1 is minus 3, and z1 is 4, and then use this condition. This is exactly similar that we have solved. So see the steps and solve this. This is the answer. This is the answer for the third problem. So this is about the conditions for a line to lie in plane, and we can solve the problems on it using these conditions. So remaining part we will continue next time. Thank you.